what we did up to now basically is, I mean, this is what we were talking right from the beginning. We said, okay, if we think about this dynamic problem in the general sense, then what we want to do is we have this dynamic system that evolves through time, and we can basically steer this dynamic system. And one of the pictures that we tried to use was like, it's like, you know, if you want to drive or if you want to program a self-driving car, right? So you can move the steering wheel. This is your control, and the state that you are in is basically the position that your car is. And what we did so far, if we want to put it in a nutshell, is basically that we were looking for an optimal plan, at least in the infinite horizon case, that we were looking for an optimal plan that maps what we want to do directly to the situation that we are in. So basically, what we this is also just related to what we just did. We had this. This is what you just plotted. We have a policy function, and the policy function is basically our plan. Okay, think of the policy function as, say, a spreadsheet with two, maybe more, but if you have one control and one state, then you have two columns. Okay, in the one column it says the situation that you are in. Okay, and the other column says what you optimally would like to do. And then the only thing you need to do is, if you want to control the system, you just look at your spreadsheet saying, okay, now I'm in the state, whatever the state is, and then I directly know what to do. This is by and large fine, and also I think a very neat way to think about dynamic problems. The problem is, if we want to go further, if we want to have more leeway on applying this to real world situation, then we obviously have the problem that what we assumed up to now is that we completely know the evolution of the system. Okay, so we exactly know if we choose our control in some specific way, then we exactly know what the situation, what the state will be in the next period of time. So, for example, we talked about the optimal consumption path. Okay, then we directly knew what would happen given that we consumed a certain amount of money. So we knew that in this situation, the wealth that we have tomorrow is just the wealth that we have today plus the income that we receive minus the consumption that we use up. But in some situations, or in many situations, a more accurate description would be that the state that we are in the next period, that this is not perfectly known. Maybe we just only have a notion, a probabilistic notion of what the state in the next period will be in. And sometimes, and this is what we will talk about later on, sometimes we also do not really have a notion in the sense of that we know a stochastic situation, a stochastic model that drives our state, but we are even more ignorant. And still we can use in this most ignorant situation, we can still use the same approach that we put forward so far to find optimal solutions. And I think this is the neat thing of everything that we talked about today. So basically, we have talked about finding the optimal control in a number of with a number of procedures, and the problem is obviously that the future is uncertain, and the way that we model uncertainty here in this case is that we assume that instead of having a deterministic law of motion, so that we exactly know the situation that we are in tomorrow or in the next period of time, that this is not that we do not know this for sure, that we do not have an exact knowledge what the state in t+1 is, but rather that we have a stochastic component. This is here denoted t+1, that we have a stochastic component, a random variable basically, that tells us the situation that we're in tomorrow, given the situation that we're in today, and given the control that we have chosen. So basically what we have in this case is, we know, okay, given the situation we are in, I know for every control and for every realization of this random variable, I know what the system or what the state tomorrow will be. Okay, and in the most simple case, we can say something about this, the stochastic properties, so to say, of this random variable. And if you look very closely to the stochastic law of motion, then you might notice that on a conceptual level, the difference to the things we did before is not too big, right? And the idea is the following. Look, suppose you knew all the realizations, okay? Then you know all the epsilons, all the epsilon path from now on until the end of your planning horizon, until the end of whatever, okay? Then you have basically here a situation where you have super many of those deterministic problems stacked together, okay? So basically, this is just, at least in this situation, a multi-dimensional deterministic problem. Okay, so the smallest part of the solution strategy will be again the same as in the deterministic case. The only difference is that we have to consider potentially many of those realization paths. Okay, and then we have to somewhat weigh them by the probability that we attach to those. Does that make sense? So basically, the difference, or the conceptual difference between the deterministic case and the stochastic case is relatively small. Okay, and this is also the reason why we spend so much time on the deterministic case, because mastering the deterministic case is basically a very important prerequisite to get a handle on the stochastic case. Okay, this is the basically the important insight. So if we have this stochastic law of motion, this is like saying I have super many deterministic law of motions for any realization path that I could think of, right? If you have questions or things that are unclear, just do not hesitate and unmute and write me over the calls. I'm happy to anything. So although at first glance those two approach or those two problems are completely different. Okay, in the one case you know everything, you know the future perfectly, what happens, and in the other case you are not really aware, or you have only a probabilistic notion of what will be. The conceptual difference is relatively small. Okay, the only thing that we have to take into account here, I mean, only is a slight understatement, so to say. The only thing that we have to take into account is that instead of choosing basically one control sequence, because we know everything what happens, we have to choose in the stochastic case a whole number of control sequences. Okay, this is what I said. You stack together basically all the deterministic problems, so you know for any deterministic problem the optimal control. But obviously, all those deterministic problems, they are not by itself deterministic, but they happen with a specific probability. Okay, so you know a number of optimal plans, and you also know a probability, or you have a probabilistic view of how important those control paths will be. So it could be the case, obviously, because as you go through the system, you learn things about the situation that you are in. So basically, this implies that the optimal control that you choose is a stochastic process. Okay, that does not mean that you are in some way time inconsistent, but you learn obviously about realizations of the stochastic process, of the things that will happen, and this makes you pick basically a different control path. Okay, so you have instead of to stay in this spreadsheet picture, the deterministic case, you have the two columns of the optimal state that you are in, and the control that you attach to this situation. Here in this case, you have basically a third column. Actually, you have more than just a third. You have many third columns, but the third column is depicts all the realizations of this random variable. And since there could be super many of those realizations, okay, you have many of those third columns. And the only thing that you have to do is you have to think about how these third columns are weighed into your objective function. Okay, this is basically what you do. Okay, so basically you could think, I mean, this is not really how we think about it, but you could think of this stochastic problem as saying, okay, look, I solve the control problem for a specific path of realizations of my random variable. We know how to do that. This is the deterministic case, and we do this basically for every realization that we could think of, and then we know afterwards basically what we have to do, at least if we put probabilistic weights on all those situations. Okay. Okay, we have some words to notation. We have here that the state that we are in tomorrow is a function of the realization of the shock of the random variable in t+1 as well. And the idea is that that once the decision maker decides on the control, okay, he or she has the information that are currently available. This is, for example, we'll see this later on, the history of the process, but this is also the state that we are in now, the current state that we are in, and choosing the optimal control, we will then, given the realization of the random variable, be aware of what the state in the next period will be. Okay, so basically this epsilon t+1 relates conceptually to the next period. At the beginning of the next period, the random variable or is realized, or there will be a realization of this random variable. Okay, so this is mainly done for notational convenience. So do not get confused that basically on this right hand side, where everything relates to now, we have this the random variable relating to the next period. Okay, this is just saying, okay, this will be the realization at the beginning of the next period, when the new planning cycle starts. Yeah. Okay. As before, we basically go through the same concepts. We start with the Lagrange approach. Again, this being said, that the Lagrange situation is not a thing that you want to do. And at least if you want to solve for the actual plan that you would follow. And the intuitive reason is also very straightforward. When we talked some 4 weeks ago or so on the Lagrange approach in the deterministic case, we said that one of the problems is that we have super many equations that we need to solve. So we had a system of equations in all the in all the states that we are in all the controls, in all the shadow values, where you have to take the law of motion into account. And think about the situation that we just talked about, that you have all the realization paths. Well, then the number of equations that you want to solve, this is basically not controllable anymore, in a sense. So we would need different methods. However, what we can do is we can, for example, describe what the optimal policy path would look like in, or what would be the optimal slope of the policy path, the thing that we called the Keynes-Ramsey rule just before. We could find this here as well. And again, this is just for you from a didactic perspective, I would say, for you to see, okay, where is the start, and what is the extension that we take into account, and how would this change basically the whole thing. Okay, and basically in the general approach is the same. So what we want to do is we want to maximize some utility function, and the utility function is somewhat described as the sum of all contemporaneous utilities up to the end of some planning horizon, capital T. It could also be an infinite horizon problem. You could discuss this here as well, but we have here the finite horizon, capital T, and we have this the stochastic law of motion. So basically, what we have here is we know what the state will be tomorrow, but only if we have an idea of what the realization will be of the shock. So what we could say, for example, is if the realization of the shock of this epsilon is such and such, we know what the state will be in. But it could also be not, it must not be, or it's not necessarily such and such. It could be also some different number. Okay, and then we have a different state that we are in. And obviously, what we could do, this is at least what we assume here, is we could attach probabilities to those realizations, which will become important later on. If we have this formulation to what we have before, obviously this does not really make sense, right? Because the objective here, so the control and the state, or the optimal control that we want to pick, and the state that we will experience through our choices, are stochastic objects. Okay, so the utility that we face is also a stochastic object. Okay, so it's not a good idea. So this is basically a random variable, right? So it's a function. So we do not want to maximize the function, but we want to pick the largest number. Okay, so we have to transform this stochastic object into something with which we can work. And what we usually do is basically following the work of von Neumann-Morgenstern, we just assume that we want to maximize the expected value of this utility. Okay, so what we basically want to do is we think of all the realizations that could happen. We attach a probability to any of those realizations. Well, and then we could basically calculate a utility function for every set of realizations. Okay, and if we weigh all those utilities for every set of realizations by their utility, we could calculate the expected utility. And this is what we want to maximize. Yeah, does that make sense? To check the time. Yeah. No one is skeptical about that? Okay. So basically what we want to do is, if we start in period 0, what we have here is basically, and this is again the neat thing in a sense, just focus on the things inside the brackets. Okay, this is basically a situation, or you could interpret, or it would be even clearer, I would say, if this is the expectation operator, right? The expectation operator conditional on the information set that you know at the beginning of your planning horizon. Okay, so I think although this is a great way of writing things up, I think many or sometimes people get confused what this really means. Okay, think of this as a sum. Okay, as a probability weighted sum. So just for the moment, just for the argument, just in your head, try to get rid of the expectation operator and write a summation sign. Okay, just for the moment. Okay, what you then have is basically a sum of all those term in brackets. And what does every part of the sum of those bracket terms means? Well, this is just one of the, you fix one realization path of every random variable epsilon. Okay, and this is part of the sum that you put into the expectation operator. So you think for the moment, okay, this inside the bracket could be interpreted as a deterministic problem, given that I know all the realizations of the random variable. Okay. The problem obviously is that you do not know those. So you want to stack those together somewhat. And the expectation operator is a way of stacking all those deterministic problems together. Obviously, they are not deterministic, right? Because it's we have a stochastic situation here, but just for the argument, okay? And no wonder this looks super similar to the things that we talked about 3 or 4 weeks ago at the beginning of the slides. If you look that up on slide 10 or so, where you have the Lagrange function and you would compare both, well, then they look very, very similar, except for the expectation operator. And the reason is that except for the expectation operator, they are very similar. Okay, this is the reason. Okay, so what you basically do is you have, this is again what I try to explain to you. You have basically this Lagrange function for any realization of the shocks that you would experience. Okay, and then aggregate all those situations that you could be in using the expectation operator. But this implies, that not only the optimal control that you choose is a stochastic variable, and the state that you are in is a stochastic variable, but the shadow value is a stochastic variable as well. So how bad you think is it to stick to the law of motion, which comes quite intuitive, right? Because depending on the realization of the shock that you would expect, well, the bindingness of the law of motion is more or less severe. Okay, you just would care less or would care more depending on the expected realization. Okay, so basically what you do, and these are I don't know, we are wrapping it up a little bit. So at least two aspects are important, and I think they are important to, or they cannot be stressed enough. The expectation operator, this E0, okay, this thing, which is conditional on the information set in 0. So you go in your mind, you go through all the realizations of the shock from now on until the end of the planning horizon. Okay, and then you think about the probability that all the shocks could have. If we have the discrete case, obviously. Okay, so then you could attach a probability weight to every realization of all those shocks. Okay, so I'm not sure whether this is a good notation, because here it's the random variable. No, it's not. No, it's not. It's a sorry. I'm sorry. My fault. So what you do is you calculate you have an idea of the probability of all the realizations, okay? And these are the probabilities with which you weigh the parts of the sum in the expectation operator in the Lagrange function, which could be complex when thinking about this. But again, from a conceptual point of view, it's not super complicated. It's just a larger sum which you weigh with those probabilities. And you are right by saying, but hey, we do not know those probabilities. Yeah, that's true. This is another issue. But suppose you knew them, well, then it would be at least thinking through it relatively easy. And another thing is that what you could do here is, obviously, you could here use this Lagrange function and choose the optimal control from today until the end of the planning horizon. But this is a different problem, right? Because then we would assume that at the beginning of the planning horizon, we want to fix to a specific control path, given all what you expect, what the realizations of the shock could be. But this is not how the world works, right? Because if you choose your control, you choose it sequentially, okay? So at every point in time, you have an information update and are able to choose the control given the then available information, okay? So this could be a case, suppose this would be this optimal consumption, this optimal consumption problem that we talked about. Then obviously you could think about an idea saying, okay, I sit down now and write down every consumption value that I want to choose optimally from now on until the end of my planning horizon. Okay, this is one way of going ahead. So you would stick always to this plan, but this is not what you would do, right? Because you would pick the control problem for the first period, and then you move through time, and then you learn something. What do you learn? Well, you learn the realizations of the shocks, of past shocks, and given those past shocks, you might want to adjust your control choice, right? You are not bound to this. At least this is what we assume, right? So basically, what you want to do, you would at every point in time, you would like to choose the control given the information set that you have then, not the information set that you have at the beginning of your planning horizon. Okay, but we see when we see this we see this clearer when we go through the first order conditions. Just a super simple example for you to see what I try to tell you all the time. This is just a very simple a very simple structure. So we do not have a real dynamic situation here. But that doesn't really matter, because this is only to show you how you how you would like to write down this Lagrange function that we had from before. So basically, what you do is there are only two values. There's only basically one shock that you consider, and this shock is also super easy because it has only two realizations. It has upper bar, epsilon bar, and epsilon underline. Okay, and both happen with probability 0.5. And what you then have is basically you have then two Lagrange problems for any realization. So basically, this part is the deterministic problem of choosing the control given epsilon upper bar, right? And this is the deterministic problem given that the realization is epsilon lower bar. And what you want to do is you want to pick a control that takes basically a compromise out of the two deterministic problems. And the compromise that you wanna pick, well, depends on the probabilities with which you weigh both deterministic situations. Again, they are not deterministic, right? Because you pick them. But this is the general idea. So what you obviously do not want to do, and maybe this was a little bit misguided at the beginning. You cannot just pick the deterministic part, or any determinist, or any realization of the random variable, call this the deterministic problem, solve this deterministic problem, and then go on, right? Because this doesn't really do, because your choice is, or you have to live with your choice, obviously, in any in any realization that the random variable will take. So you want to take this into account, right? But the general idea is the same. So instead of picking the optimal control in 0 as a function of the S, this is also a function of the realization of the random variable, and well, of the probabilities. Well, it's not really a function of the probabilities, but this is the additional information that we have. So what we could do is we could basically treat this shock as an additional state, and this is exactly what we are going to do. Okay, this is later on the exact same approach that we are trying to follow. So basically, what again, the operative approach in the deterministic case is very, very helpful to extend this to stochastic dynamic optimization problems. Okay, so I think time is up. We will talk a little bit about the Lagrange solution strategy on Thursday, and I think then we will take maybe Thursday and a little bit of the week after that to talk to use the Lagrange and then the Bellman equation approach. And then we implement the numerical things, and then I think then it's more it's already Christmas, no? I guess maybe there's 1 week left, but yeah, thanks for now. Next week we'll talk about the Lagrange and the Bellman thing, and then we talk about numerical implementations of the stochastic case, and then we will see what happens next. Okay, thank you so much.